As we have discussed in the previous video of electrochemistry, electrochemistry is the interconversion of electricity and redox reaction. For the interconversion, we require some device. For the conversion of electricity to redox reaction, electrolytic cell is used, and for the conversion of redox reaction to electricity, electrochemical cell is used. Electrolytic cell uses electricity to facilitate non-spontaneous redox reaction. We have discussed electrolytic cell in the previous video of electrochemistry. In this video, we are going to discuss electrochemical cell. It uses spontaneous redox reaction to produce electricity. So let's try to understand what is spontaneous redox reaction. When you add zinc to copper sulfate solution, zinc displaces copper from copper sulfate. You must have done this experiment in lower classes. So let's write the reaction for this change. When we add zinc to copper sulfate, you will get zinc sulfate plus copper. Now write the oxidation number of copper. SO4 ion carries -2 charge, so oxidation number of copper will be +2. Oxidation number of an element in its standard state remains 0. So the oxidation number of zinc will be 0. In zinc sulfate, again sulfate carries -2 charge, so zinc will carry +2 charge and the oxidation number of zinc will be +2 and oxidation number of copper will be 0. Increase in oxidation number is the oxidation and decrease in oxidation number is reduction. Oxidation number of copper changes from +2 to 0. So copper get reduced from +2 to 0. Oxidation number of zinc changes from 0 to +2. So zinc get oxidized. Oxidation is loss of electron and reduction is gain of electron. So there is a flow of electron from oxidation reaction to reduction reaction. In electrochemical cell, oxidation and reduction reactions are physically separated so that we can use the flow of electron to generate electricity. For the construction of electrochemical cell, 2 electrodes are taken. One is oxidation electrode and other one is reduction electrode. In oxidation electrode, zinc electrode is dipped in zinc sulfate solution. And for reduction electrode, copper electrode is dipped in copper sulfate solution. Oxidation electrode is also called as anode. As we have discussed in our previous video, anode is the electrode where oxidation takes place. And reduction electrode is also called as cathode. So cathode is the electrode where reduction takes place. In oxidation electrode, oxidation takes place. So zinc metal from the electrode loses electron and get converted into zinc 2+ ion. As it loses electron to the electrode, this electrode becomes electron rich. As it becomes electron rich, negative charge developed at anode. And in case of reduction electrode, reduction takes place at this electrode. Copper 2+ ion gains electron from this electrode and get deposited in the form of copper. As electrons are gained from this electrode becomes electron deficient, and that's how cathode develops positive charge in electrochemical cell. Cathode is always reduction electrode and anode is always oxidation electrode, whether it is electrochemical cell or electrolytic cell. But in case of electrochemical cell, cathode is positive and anode is negative, while in case of electrolytic cell, cathode is negative and anode is positive. This difference is due to the spontaneous and non-spontaneous redox reaction. As anode is electron rich, it supplies electron, and as cathode is electron deficient, it receives electron. So there is flow of electron from anode to cathode, and current flows from cathode to anode, as the flow of current is opposite to the flow of electron. So this flow of current can be used to generate electricity. In the oxidation half cell, concentration of zinc 2+ ion increases, as there is continuous conversion of zinc metal to zinc 2+ ion that added to the zinc sulfate solution. So why would it allow electron to go out from the circuit? Similarly, in the reduction half cell, concentration of copper 2+ ion decreases and sulfate ion increases because there is continuous conversion of copper 2+ ion from the electrolyte to copper metal. So why would it allow electron to come in the reduction half cell? And how would current flow when the circuit is incomplete? As the solution of all these questions, salt bridge is used. Salt bridge is an U2 containing solution of inert electrolyte such as KCl or ammonium nitrate and 5% agar solution. So what is the role of salt bridge? Anions of salt bridge deliver electron to zinc 2 plus ion, or you can say to the oxidation half cell. That's how they neutralizes the solution present inside the oxidation half cell. In the same way, cations of salt bridge receives electron from sulfate ion, and that's how they neutralizes the solution present inside the reduction half cell. That's how salt bridge complete the circuit, as it contains electrolyte that allow electron to pass through it. And it also maintains the electrical neutrality of both the half cell without mixing of ions. We know current flow across the potential difference, but how is potential difference developed in electrochemical cell? When you closely observed oxidation half cell, anode is electron rich, so positive charge will gather around the electrode. Similarly, in case of reduction half cell, cathode is electron deficient, so electrons will be gathered around the electrode. And due to difference in charge at interface, potential is developed at each electrode. And this potential is called as electrode potential. So that's how electrode potential is developed at each electrode. Now current will flow across the potential difference. Electrons flow from anode to cathode, as anode is electron rich, and current flows from cathode to anode as the flow of current opposite to the flow of electron. Now come to the cell reaction. Now let's write the reaction take place at anode. At anode, zinc get oxidized by the loss of 2 electrons and converted into zinc 2 plus ion. So you will get the reaction zinc solid gives zinc 2 plus ion plus 2 electrons. Now write the reaction take place at cathode. At cathode, reduction take place. So copper 2 plus ion gains 2 electron and converted into copper solid. To get the complete cell reaction, we need to add both the reaction take place at anode as well as on cathode. So when you add both the reaction, electrons and electron will get cancelled out and you will get zinc plus copper 2 plus ion gives zinc 2 plus copper. This specific arrangement of electrode, zinc electrode and copper electrode with the solution zinc sulfate and copper sulfate is called as Daniell cell. Is there any way to provide the information about cell without giving the cell reaction or cell diagram? By cell notation, we can provide all the information about the cell without drawing its cell diagram. Cell notation tells you about the composition of oxidation and reduction half cell. It also provides the information about the concentration of electrolyte used. So let's see how we can write the cell notation for Daniell cell. First of all, write the reaction take place at anode. So you will get zinc gives zinc 2 plus 2 electrons. Now write the reaction at cathode. So here you will get copper 2 plus 2 electrons gives copper. Now add both the reaction to get complete cell reaction. So here you will get zinc plus copper 2 plus ion gives zinc 2 plus copper. In cell notation, first of all we will write anode, then we will write information about cathode. And there is a salt bridge between anode and cathode that is denoted by double line. Now we will write the information about anode. At anode, zinc converts into zinc 2 plus ion. Zinc is present at the electrode and zinc 2 plus ion present in the electrolyte. So there is phase difference. Zinc is in solid state and zinc 2 plus ions are in aqueous phase. So there is a phase difference between zinc and zinc 2 plus ion. So we are going to separate them by a vertical line. Now write the information about cathode. At cathode, copper 2 plus ion converts into copper. Copper 2 plus ions are present in aqueous phase and copper is present in solid phase. So again there is a phase difference between copper 2 plus and copper. So again we are going to separate them by a single vertical line. Now draw the salt bridge between anode and cathode by double vertical line. So in cell notation, single vertical line represents phase boundary and double vertical line represents salt bridge. Now, if we take the concentration of zinc sulfate and copper sulfate solution at 1 molar, to include this information in the cell notation, you have to write 1 molar in place of aqueous. So here you will get zinc solid vertical line, zinc 2 plus ion, and the concentration of zinc 2 plus ion which is present at aqueous phase is 1 molar. Then salt bridge, copper 2 plus ion that is also present in aqueous phase and its concentration is 1 molar. Then vertical line and copper. Now this is the complete cell notation which provides the information about electrode, electrolyte and their concentration as well. Now let's try to read the cell notation. As we have learned earlier, anode is always written on the left side of the cell notation and cathode is written on the right side of the cell notation. So this part is anode and this part gives the information about cathode. At anode, Mg converts into Mg2 plus ion and at cathode, Ag plus ion converts into Ag. Here oxidation number of Mg is 0 and oxidation number of Mg2 plus ion is plus 2. And we know increase in oxidation number is oxidation. So this is the oxidation reaction. Oxidation number of Ag plus ion is plus 1 and oxidation number of Ag is 0. So there is decrease in oxidation number and decrease in oxidation number is reduction as reduction take place at cathode. Now write the reaction take place at anode. So here you will get Mg gives 2 electron plus Mg2 plus ion. Similarly write the reaction take place at cathode. Here Ag plus ion gains 1 electron and gives Ag. Now we need to add both the reaction to get complete cell reaction. But before that you have to balance the electrons. As 2 electrons are produced in oxidation reaction, 2 electrons must get consumed in the reduction reaction. So here you have to multiply this equation by 2. So you will get 2Ag plus 2 electrons gives 2Ag. Now add both the reactions. On adding both the reaction, you will get Mg plus 2Ag plus gives Mg2 plus 2Ag. This is the complete cell reaction that we have derived from the cell notation. Concentration of electrolyte used in anode is 1 molar and for cathode it is also 1 molar. Now let's try to understand more about electrode potential. Electrode potential is the difference developed between electrode and electrolyte. When concentration of all the species involved in a half reaction is unity, then the electrode potential is known as standard electrode potential. By IUPAC convention, standard reduction potential is now called as standard electrode potential. So according to IUPAC convention, anode has negative potential with respect to the solution and cathode has positive potential with respect to the solution. Because at cathode reduction take place and at anode oxidation take place. Potential of individual cell cannot be measured. We can measure only the difference between them. So we cannot measure electrode potential of anode or cathode, but we can measure the difference between them. The potential difference between two electrodes is called cell potential and it is measured in volts. Experimentally, it is measured by the voltmeter. Another common term for cell potential is electromotive force, or in short you can say EMF. Cell potential not only depends on the nature of electrode and ions but also on the concentration of ions and temperature at which cell is operated. So as we have learned, cell potential is the potential difference between two electrodes. So you will get the equation E naught cell is equal to E naught cathode minus E naught anode. As it is the difference of electrode potential of cathode and electrode potential of anode. Its value may be positive, If its value is positive, then cell will work. And if its value is negative, then cell will not work. So you won't get any current from the cell. But if its value is 0, that means cell is at equilibrium. In case of Daniell cell, when the concentration of copper 2 plus and zinc 2 plus ion both are 1 molar, cell potential of Daniell cell is found to be 1.1 volt at 25 degrees centigrade. So by voltmeter we can calculate the E cell. And if we know either of the electrode potential, we can calculate the another one by subtracting it from the E cell. So let's place the value of E cell obtained for Daniell cell in this equation. So here you will get 1.1 volt is equal to electrode potential of cathode minus electrode potential of anode. If we know the electrode potential of cathode, we can calculate the electrode potential of anode by subtracting the electrode potential of cathode from E cell. But it is impossible to measure the potential of just single electrode. So how to determine the electrode potential? If we arbitrarily set the potential value of a particular electrode at 0, we can use that electrode to determine the relative potential of other electrodes. This particular electrode is called as reference electrode. SHE is used as a reference electrode. SHE is a standard hydrogen electrode. In this standard hydrogen electrode, hydrogen gas is bubbled at 1 atmosphere pressure to 1 molar solution of HCl at 25 degrees centigrade. And here platinum electrode is used. This platinum electrode provides the surface on which dissociation of hydrogen molecule takes place that we have bubbled through the electrode. So H2 gas dissociates into 2H plus ion and gives 2 electrons. Platinum electrode also serves as an electrical conductor to the external circuit. Under standard conditions, when the pressure of H2 is 1 atmosphere and the concentration of HCl solution is 1 molar, the potential for the reduction of H plus ion at 25 degrees centigrade is taken exactly 0. When you write the reduction reaction for H plus ion, you will get 2H plus ion plus 2 electrons gives H2. Now let's try to write the cell notation for this electrode. So here H plus converts into H2. So here you will get H plus ion, then place a vertical line, then write H2. H2 is gas and its pressure is 1 atmosphere. H plus ion is present in aqueous phase and H2 is a gas. So there is a phase difference. So here you have to place one vertical line that represents the phase boundary. Now here platinum electrode is used and it is in solid state. So again there is a phase difference between hydrogen gas and platinum electrode. So again place a vertical line between them. So this is the complete cell notation for SHE. So let's see how we can use SHE to determine the electrode potential of other electrodes. For example, if we want to measure the electrode potential of zinc electrode. As we know, we can measure the cell potential, but we cannot measure the absolute value of electrode potential. We have the equation E naught cell is equal to E naught cathode minus E naught anode. So here we are going to make cathode out of SHE and anode is made up of zinc electrode. So let's rewrite the equation. So here you will get E naught cell is equal to E naught SHE as cathode is made up of SHE minus E naught zinc electrode. In zinc electrode, though the oxidation takes place and zinc converts into zinc 2 plus ion. But in the formula I have used zinc 2 plus ion oblique zinc. Because as per the IUPAC convention, standard reduction potential is considered as standard electrode potential. So that's why you have to write it in the terms of reduction. And reduction is the decrease in oxidation number. That's why I have written here zinc 2 plus ion oblique zinc. By using voltmeter, its E naught cell is found to be 0.76 volt. Now place the value in this formula. So here you will get 0.76 volt is equal to 0 as the standard reduction potential of SHE is 0 minus E naught zinc electrode. So when you solve it, you will get E naught zinc electrode will be equal to minus 0.76 volt. Now write the cell notation for this cell. As we know, first you have to write anode, then you have to write information about cathode, and anode and cathode are separated by salt bridge. At anode, oxidation takes place and zinc converts into zinc 2 plus ion. So here you will get zinc phase boundary, zinc 2 plus ion, and the concentration of zinc 2 plus ion is 1 molar. Salt bridge. At cathode, reduction takes place and H plus ion converts into H2 gas. So here you will get H plus ion, its concentration is 1 molar, phase boundary, H2 gas at 1 atmosphere pressure, then again phase boundary, platinum electrode in solid state. So this is the complete cell notation for this cell. Now let's use SHE to determine the electrode potential of copper electrode. Again we need to construct a cell. This time we are going to make cathode out of copper electrode and anode is made up of SHE. We have the equation E naught cell is equal to E naught cathode minus E naught anode. Now let's rewrite the formula. So here you will get E naught cell is equal to E naught copper electrode minus E naught SHE. By voltmeter we can calculate the E naught cell and it is found to be 0.34 volt. So now place the value in this formula. So here you will get 0.34 volt is equal to E naught copper electrode minus 0 as the standard electrode potential of SHE is 0. On calculating you will get electrode potential of copper electrode is equal to 0.34 volt. Now let's write the cell notation for this cell. Here anode is made up of SHE and cathode is made up of copper electrode. First we are going to write the information about anode, then we are going to write information about cathode. Anode and cathode are separated by a salt bridge. So first write the information about anode. At anode, oxidation takes place. So at anode, H2 gas will convert into H plus ion. And at cathode, reduction takes place. Here copper 2 plus ion converts into copper. So here you will get H2 gas at 1 atmosphere pressure, then single vertical line to separate the phase, then H plus ion concentration at 1 molar, single vertical line to separate the phase as platinum electrode present in solid state. Then place a salt bridge, copper 2 plus ion and the concentration is 1 molar. Then single vertical line to separate the phase, then copper solid. So this is the complete cell notation. So that's how electrode potential of different electrodes are measured by using SHE. And here is the list of electrode potential of different electrodes. When you observe the values given in this table, you will see SHE has 0 potential. And when you observe below 0, negative value of electrode potential increases. And the maximum value is found to be minus 3.05 and it is for lithium. And above SHE, positive value increases and increases up to 2.87 and it is for fluorine. The more positive value means greater tendency of the substance to get reduced. In this table, fluorine has the maximum value and it is 2.87. Equation is given for reduction. F2 plus 2 electrons gives 2F negative and its E naught value is equal to 2.87 volt. It means forward reaction is favored and forward reaction is the gain of electron means reduction reaction is favored. Means fluorine has more tendency to get reduced. As it undergo reduction, it is a strong oxidizing agent. More negative value means lesser tendency for the substance to be reduced or it has greater tendency to be oxidized. When you observe in this table, lithium has the maximum negative value and it is minus 3.05 Here you will get the equation Li plus electron give Li, and its value is minus 3.05 volt. Negative value of E naught. Element favored backward reaction more as compared to forward reaction. Forward reaction is the reduction reaction and backward reaction is the oxidation reaction. So it has more tendency to be oxidized. As it has more tendency to get oxidized, it will act as a strong reducing agent. On changing the stoichiometric coefficient of a half reaction, it doesn't affect the value of E naught. For example, for fluorine, E naught value is 2.87 given in the table. So if we multiply this half reaction by any number, it doesn't affect the value of E naught. It will remain 2.87 volt. Because electrode potential is an intensive property, it doesn't depend on the concentration of ions involved in half reaction. But on changing the direction of half cell reaction, sign of E naught changes, but the value of E naught remains same. For example, for the reduction of F2, its value is 2.87 volt. On changing the direction of this half reaction, you will get 2F negative gives F2 plus 2 electron. This reaction is for reduction reaction and this reaction is for oxidation reaction. For reduction, its value is 2.87 volt, and for the oxidation reaction, its value becomes minus 2.87 volt. So there is only change in the sign, but the value of E naught remains same.